evening or good morning everyone. This is Dr. Nat. We are doing Computer Organization and Architecture ECC 3204-1 and this is lecture number 2. So we are going to talk about computer evolution and performance for today. So let's do a little recap before we start with that. So last time we talked about how computers have become part and parcel of our daily lives. They are everywhere in the form of embedded systems. You have them in your smartphones, you have them in your smartwatches. I don't have one. You have them as sensors that track your breathing, sensors that track your oxygen saturation in your blood, sensors that track your heartbeat in the form of a watch. That's amazing. And we have other intelligent appliances that is not wearable, such as your systems at home that can control the lighting, systems at home that can control your washing machine and stuff like that. Now, it is very interesting on how these things work, and it is important for us as computer engineers and also communication engineers to understand how computer works. So what is inside the computer and how does it work? So this course is going to talk about that. And we need to distinguish. First, we need to distinguish between two terms, which is the topic of our course, which is computer architecture and also computer organization. And I talked about this last time, right? And I hope you still remember when we talked about what computer architecture was. It was what the features that are offered or what are the features that we see being delivered by the computer. So here, computer architecture is how to integrate the components to build a computer system to achieve a desired level of performance. The desired level of performance is the features that I was talking about. And you can think of this such, imagine you are building a house, right? So to build a house, you first start with what do you want from your house? How should your house look like? You want three bathrooms, you want one kitchen, and maybe you want a very big living room for guests and a small living room for personal use, for family use, right? So this is what you want from your house. You want your house to deliver that to you, right? So what do? You hire an architecture that designs your house, the floor plan, the layout, and how it should look inside. So that's your architect. It does that for you. And it visualizes what your house is going to look like and what your house features, right? But who actually builds the house? It is the civil engineer. So the civil engineer has to calculate what is the tolerance to build your house, how much bricks is needed, how many tiles is needed, what is the wiring like, what is the plumbing like. So the civil engineer has to figure out how to integrate all of this, and he does this behind the scene, like I mentioned to you before. So you have on one end, you have the civil engineer trying to build everything from scratch. This is the components that build the computer. And you have the other, which is the architect, that visualizes what the house should look like. And this is the computer architecture. It tells you what this computer can do for you. Okay, so that's enough recap for now. Okay, so for chapter 2, we are going to dive in the history of computers. So we are going to talk about the first generation of computers, and it was based on the vacuum tubes. And then we're going to talk about the second generation of computers, which was based on transistors. And from transistors, we were led into the miniaturization, or you make it into very small scale computers, which we know as integrated circuits now. And then we are going to talk about the performance designs in terms of the microprocessor speed, the performance balance, the chip organization, and also the architecture. And then we have the multi-core, MICs, GPUs, evolution of Intel x86, embedded systems, ARM evolution, performance assessments such as clock speed and instructions per second. We have the benchmarks, Amdahl's law, and also Little's law. So I don't think we are going to finish everything in one lecture. So I'm going to break this into two parts, alright? Okay, so this is a vacuum tube. We're going to start with the first generation of computers. Bear with me, it's historical. Some of you don't really like history, but we have to learn this. So the first generation is called, is based on vacuum tubes. So this is a picture of vacuum tubes. It looks like, what does it look like? It looks like your light bulb, does it not? Actually, your light bulb is quite similar to a vacuum tube in a sense that in your light bulb is also a vacuum, and only in that vacuumed environment is it able to light up. And if your light bulb is broken, then the filament won't work because it has to work inside a vacuum. So when it is inside a vacuum, the vacuum tubes actually use a lot of powers, hundreds of watts, and what happens is that the filament, or like the metal that they use inside this vacuum tube, is heat up in a way that electrons are flying all over from the metal plate. They fly all over, and they need a positive place or a positive plate to be attracted to. So this is how the vacuum tube works. When they put in a plate, what you get is electrons moving from the negative to the positive, and you get a complete circuit and it lights up, right? Okay, so that's basically like a general overview on how vacuum tubes work and how it is similar to a light bulb, in case you want to relate to it. So the vacuum tubes, with the invention of vacuum tubes, they also came up with something called the ENIAC, ENIAC, Electronic Numerical Integrator and Computer. So you see that there is a word numerical integrator, and I told you before that the first mechanical device that was considered a computer was actually a calculator. But they don't call that computers. ENIAC is the first generation computer. Okay, so it is designed and constructed at University of Pennsylvania, which is in the US. It started in 1943 and completed in 1946. So why was ENIAC invented in the first place? It was to help the ongoing war at the time. However, ENIAC was quite late to be finished, so it couldn't help the war in a sense that it could not predict how the weapons trajectory, how the weapons would shoot. It was supposed to help in that sense, but because it was finished late, so the ENIAC was not used for war. It was not finished in time to be used in war effort. Its first task was to perform a series of calculations that were used to help determine the feasibility of the hydrogen bomb. So it was used for bombs as well. And this was funded by the US Army, of course, and it continued to operate under BRL management until 1955, when it was deassembled. Okay, so this is how like the cartoon version of ENIAC looks like. It's very, very big. Let me tell you how big it is. It weighed 30 tons. That's very heavy. Occupied 1,500 square feet of floor space. Do you know how big that is? It's as big as a condominium. The typical condominium that we have, 1,500 square feet. It's that big. And then it contained more than 18,000 vacuum tubes. So imagine you have 18,000 light bulbs working to operate this. But it's not a light bulb, it's a vacuum tube. It's different. And then it used 140 kilowatt power consumption. That is a lot. And then capable of 5,000 additions per second. That is like way beyond a calculator. And then it worked in decimal rather than a binary machine. Our machines now work in zeros and ones, but previously it was in decimals, which is tens. And then the memory consisted of 20 accumulators, each capable of holding a 10-digit number. So major drawback was the need for manual programming. So you can imagine right now, our computer, we just click on it and it knows what to do because it already has that programmed instruction. We don't have to like code to tell it what to do because there is a program already inside our computer. There's already a set of instructions written by someone else for us, right? So ENIAC was not like that, in a way that you had to type in your own instructions or program by setting switches and unplugging cables. So it was a lot of work. It had the potential, but not everyone was smart enough to do this, right? So it was like very, I would say the application was not wide enough for the mass to use it. And then came John von Neumann. This guy is a Hungarian, John von Neumann. I hope I'm pronouncing that right. I actually googled his name. ADVAC. He is considered like the person behind this technology, which is electronic discrete variable computer. This came after ENIAC, ADVAC. Okay, so behind him is the computer, very unpleasant looking, but it works. Okay, so after the ENIAC came in the ADVAC. The ADVAC is actually electronic discrete variable computer. So the great thing about ADVAC as compared to ENIAC was that it was able to store programs. So that was like great news, right? It was able to store program concept, and it was attributed to the ENIAC designers because, of course, it was the ENIAC designers who knew what was the problem with the ENIAC and how they should fix it, right? Most notably, the mathematician John von Neumann. He was a Hungarian guy. So the program represented in a form suitable for storing in memory alongside the data. At the same time, there was the development of Ias computer. So it was developed in Princeton Institute for Advanced Studies. The prototype of all subsequent general purpose computers was developed, and it was completed in 1952. So this is the structure of the von Neumann machine. So you have your main memory here, and inside your main memory you would have your primary memory and also your secondary memory. And then it was connected to the arithmetic logic unit, which does the processing, and you have the program control unit, which controls and delivers the it uses the instructions, right? You have data and you have instructions. So the data was used by the ALU, the arithmetic logic unit, whereas the instructions in the main memory was used by the control unit to execute the programs. And it was interfaced with the I/O equipment for input and output for the movement of data. So this is the structure of the Ias computer, which was based on von Neumann, the mathematician guy. Okay, so let's talk about the Ias memory formats because it's quite interesting. The memory of the Ias consists of 1000 storage locations, or you can call this as words, instruction words. So the instruction words has 40 bits. You can look over here, it has 40 bits. If I divide it into two, you have left instruction on one side and right instruction on the other side, which means that the left instruction has 20 bits, the right instruction also has 20 bits, so you have the 40 bits altogether. So 40 bits is instruction word, one instruction word. So you have your opcode over here. What is opcode? It is your operation code. For example, you want to do addition of some data with another data. So that is your opcode, and then this is the address of which you will be doing this operation. So you can see that the opcode begins from 0 to before 8, which is 7. So I'm assuming that this is 8 bits, right? And because we know that this is 20, this is 8, so your address is 12 bits. And your opcode again is 8 bits. And then you have this one with 12 bits. So you see that even though it is 40 bits, it ends at 39 because you start at 0 as compared to when you start at 1, you end at 40. But when you start at 0, the 0 is counted as a number, so you end at 39. So the length is 40 bits. That is one instruction word. Okay? So numbers are represented in binary form, and each instruction is in binary code. So this was different, very different from ENIAC in a way that ENIAC was in decimals, in tens, right? Okay, so the Ias structure that I showed you earlier was the basic one. So if we were to expand it, we still have the main memory, and we have the input-output equipment, and the CPU is very much extended, right? It's blown up. So we still have the ALU and the program control unit, and these two are under the CPU. Let's look back at the basic one. So this was your, whoops, let's go back. So this is your CPU over here. You have your ALU and you have your program control unit. So let's look at the expanded one. So this is your ALU and this is your program control unit. So inside your ALU and inside your program control unit are registers. So you have your AC, accumulator, and this is multiplier, MQ is multiplier quotient. These are all operations that enable you to do addition and multiplication, right? So they belong in the ALU. And then you have your MBR, and then you have your IBR, PC, you have your MAR, IR, and then you have your control circuit. So let's take a look on what these short forms mean. So you have your MBR, which is the memory buffer register. It's a type of register. You have your memory address register, MAR. You have your instruction register. So anything with the R is register. Instruction buffer register, R. You have your accumulator and multiplier quotient. That one I remember because it was the easiest one to remember. And then the program counter is PC. Now let's take a look at the expanded version again. So this is your accumulator. Multiplier quotient belongs with the ALU, and this is your register. I still can't remember what MBR is. This is a register, and this is your program counter. Is it important for you to remember all this? Just the gist of it. I would say that you would have to approximately understand what ALU is for and what does a control circuit, what a program control unit does. Okay, but the short forms, not so much. Okay, maybe in later lectures, yes, but what is important to know now is that the existence of registers in the ALU and also in the program control unit. Okay, so after ENIAC, after ADVAC, and which came the Ias computer structure, we have the commercial computers ready for the mass. So UNIVAC 1, which is the Universal Automatic Computer, which means that you did not have to manually program the computer. It was the first successful commercial computer. It was intended for both scientific and also commercial applications. It was commissioned by the US Bureau of Census for 1950 calculations. So who made this? It was Eckert and Mauchly, and they formed their own company. Very awesome. And came after UNIVAC number 1, came in UNIVAC number 2, which was delivered in the late 1950s. It had a greater memory capacity and also higher performance. So later on, after Eckert and Mauchly launched their UNIVAC, IBM came as the major manufacturer of punch card processing equipment. How does that work? Why is my writing in white? Let me edit that for a bit. Okie dokie. Let's go back to our not this one. Yeah, IBM. Okay, so we were talking about Eckert and Mauchly, right? Eckert and Mauchly created the UNIVAC number 1 and number 2. Very great for scientific and also commercial applications. And then came in IBM. IBM was another company which was the manufacturer of punch card processing equipment. What does that mean? It means that if the punch card had holes, right? And when they slot in the punch card, it was able to give instructions to the machine. For example, I have, let me draw something. Ooh, I have a pen over here. Okay, so I have this punch card. This punch card belongs to me. I make these holes. My hole is like this, for example. And in my class, we have another person called, I still don't remember your names. Let's say Faidi. So Faidi's card is like this. Okay, so we have two different cards. When I slot in my punch card, I tell what the holes do is that it tells my machine let's say we're talking about like a sewing machine, right? We are working in a factory for clothes, and this is my punch card. So I slot in my punch card, and what I do is I'm telling the machine, hey, this is my instruction. I want you to sew clothes for girls. That was the instruction. And then came in Feidi. Feidi said, okay, your turn is up. This is my turn now. So I'm going to slot in my punch card. And what the punch card does to the machine is that it tells the machine how it should behave. It was some sort of like a coding, right? These holes tells the machine how to behave or what to deliver. It was something like codes, but in the form of holes. So that was what IBM was doing. So Feidi puts in this punch card. What it does is the machine now sews clothes for boys. What's the difference between boys and girls' clothes? The cutting, obvious. But really, I don't know. Actually, I don't know. I don't know about textile much. But that was an example. So IBM was the manufacturer of punch card processing equipment. So it delivered. Because of this capability, they were able to come up with its first electronic stored program computer in 1953. So it was intended primarily for scientific applications, and it introduced 702 product in 1955. The hardware features made it suitable to business applications. It was already a big company. So compared to a startup, of course, like the big company would like have the upper hand, right? Because they are able to have a lot more money to invest into what they want to do. So a series of 700 to 7,000 computers established IBM as the overwhelmingly dominant computer manufacturer. Okay, so great news. That was the end of the first generation of computers based on vacuum tubes. So came in the second generation of computers, which is based on transistors. So we have much more to discuss. So why transistors? It is smaller, it is cheaper. Of course, cost always plays a big role in anything. It dissipates less heat than a vacuum tube. Very, very great news. You don't have to have a lot of area to dissipate heat, right? So you can make it smaller. And is a solid state device made from silicon. Was invented at the Bell Labs, of course, in 1947. It was not until the late 1950s that fully transistorized computers were commercially available. So yes, of course, they already invented the transistors, but it was not later that transistors were fully used in computers. They knew how good it was, but of course that transition takes some time. So the use of transistors defines the second generation computers. So it has become widely acceptable to classify computers into generations based on the fundamental hardware technology. For example, as we can see here in table 2.2, each new generation is characterized by greater processing performance, larger memory capacity, and also smaller size than the previous one. So size, processing, and memory. Size, processing, and memory. So if I ask you, what is the difference between these generations of computers, you should give me these three answers: the size, the processing, and also the memory. So it's faster in processing, it has larger memory, it is smaller in size. So from 1946 to 1957, we have the vacuum tube, which was the typical speed was 40,000. And then came after that was the transistor, the second generation computer, 240,000. How much is that? It's times by 5. Whoops. It's times by 5. And then after that, small and medium scale integration. What would you call this? You call this as SSI and MSI. Small scale integration and MSI. Why am I showing you this short form? Bear with me. So 200,000 operations per second to 1 million. So again, times 5. Pretty cool, right? And then you have your large scale integration called LSI. Now it is times by 10. Now it's rapidly evolving. And then times by another 10, right? Whoops. Very large scale integration. Now, do you recognize this? VLSI. I hope you recognize this because it's very famous. VLSI. What does it mean? Very large scale integration. And it is able to perform 100 million operations per second. And then currently we are still in the ULSI, ultra large scale integration. ULSI. So this one is another times 10. Okay. Alright. So second generation computers, more complex arithmetic and logic units, and also control units, the use of high-level programming languages. Previously, it was just binary, and it was assembly language and machine language. Now, we use high-level programming language. The provision of system software which provided the ability to load programs, right? Move data to peripherals and libraries. Remember what I told you about peripherals? It is your equipment that is next to your computer, such as keyboard, such as mouse, and libraries, and also perform common computations. Okay, so this began the mini computer phenomenon. So everyone was like racing, making the computer as small as they can. That would become so prominent in the third generation. So we have not touched the third generation yet. So the second generation is noteworthy also for the appearance of the Digital Equipment Corporation, DEC. Okay, so that is it. So here is a table, example members of IBM 700/7000 series. We have the 701, which used the vacuum tubes, and 704 also used vacuum tubes, and then we have 709, still vacuum tubes. We have the 7090, so they added another digit to this to represent now that the CPU technology is based on transistors. So you transition from 700 to 7000, at least for IBM. That was what they were doing. They were manufacturing hardware for computers. And you can see that the cycle time becomes faster, and the memory size becomes greater. And the number of opcodes, the operations that they can perform at a time, is increasing. The number of index registers, we talked about registers before, also increases. They can store more because now everything is smaller, so they have more space to put in more stuff, right? And then what is important here? I think we are good. Moving on. So this is the 7094 configuration. Let's not talk about this one yet. And then let's go to the third generation, which is based on the integrated circuits. Hooray, we are finally here, which is what we're dealing with. So first, in 1958, the invention of integrated circuits. So first we began with a single self-contained transistor. Pretty sad, right? So it was manufactured separately, packaged in their own containers, and soldered or wired together onto masonite-like circuit board. So it was on the circuit board individually. That was how it was. And then manufacturing was expensive and also very tedious, cumbersome. So the two most important members of the third generation were IBM System and also DEC. DEC is also a company, so maybe their rival, right? Okay, so now we have to talk about microelectronics when we are talking about the third generation computers. Why? Because as everything becomes smaller, the electronics has to follow through as well, right? So microelectronics literally means small. What was that? Small. How do you make small? This is small. Small electronics. Since the beginning of the digital electronics era and the computer industry, there has been persistent and consistent trend towards the reduction of the size, right, in digital electronic circuits. So the basic elements of a computer, as we talked about in lecture number 1, was that we need to have memory, we need to have storage, which is memory, we need to have movement of the data, we need to have processing, and also we need to have control. So we have 4 basic elements of a computer: storage, movement, processing, control. Right? So to do these 4 elements, or to have these 4 elements of a computer, you need to have 2 components, 2 electronic components. The first one is called the gate. So the gate, let me try to remember this. So a gate is a device that implements a simple Boolean logic function. For example, if A and B are true, then C must be true. So that is like an example of a Boolean logic function. I believe you've seen this type of logic before. So it is called gates because it flows in the same way as a canal gates flow water. So if it is not true, it's not going to open. If it is true, it's going to flow, it's going to open, and the water can flow. So it acts like a gate to the water. So this is not like that. It's supposed to be like this, right? Because water flows like this, upwards. And then we have our memory cell. So a memory cell is a device that can store 1 bit of data. That is, the device can be one of 2 stable states at any time. So binary, right? Binary, you have 2 states, either a 0 or a 1. Either a 0 or a 1. So it can be only either one of these stable states at a time. So by interconnecting large numbers of these fundamental devices, so if you have a lot of gates and a lot of memory cells, we can construct a computer successfully. Okay, so we can relate this to our basic 4 elements, or the 4 capabilities of a computer, which is data storage, data processing, data movement, and also control. So data storage is provided by the memory cells of integrated circuit. Then we have the data processing provided by the gates. Remember, if A and B are true, then C must be true, open. Or if it's not true, then it stays closed. So this is where the processing happens, at the gate. And then we have the data movement, which is the path among components that are used to move data from memory to memory, or sometimes there is a gate in between the memory whereby the memory has to go through the gate. So you have your memory, gate, and memory over here. So that is your data movement. And then we have the control, which is the path among components that carry control signals. For example, a gate, let's just imagine this is a gate, will have 1 or 2 data plus a control signal that activates the gate. So you need to have 1 or 2 data plus a control signal to activate the gate. So the gate needs to process stuff, right? So it has to have some it has to have some data to process, and it has to have some control for it to be activated. Alright, so a computer consists of gates, memory cells, and interconnections among these 4 elements. The gates and memory cells are constructed of simple digital electronic components, and it exploits the fact that such components as transistors, resistors, and conductors can be fabricated from a semiconductor such as silicon. So many transistors can be produced at the same time on a single wafer of a silicon, we will see in a bit, and then the transistors can be connected with a processor metallization to form circuits, which we see in our regular circuits on our chip. We see that there is like a metallic path between the components because they want to, form the circuit, right? So this is your packaged chip. This is your packaged chip. So hard to pronounce. This is your chip. Inside your chip, it is made out of wafer, and on top of the wafer, we have like the gates, and then you package it nicely. Okay. A thin wafer of silicon is divided into a matrix of small areas, and then the identical circuit pattern is fabricated in each area, which means that they are basically duplicating the design on each small area. And the wafer is broken up into chips. So you have your one big wafer, it's divided into small areas. They duplicate the design on each area. They cut the wafer into smaller bits, and you have your multiple chips. So each chip consists of many gates and memory cells. Of course, remember when we were talking about microelectronics, we have two components that makes up the computer for our integrated circuit, which is memory cell and gate, right? And they give us the 4 functionalities when integrated together. So the chip is packaged in a housing that protects it and provides pins for attachment. So you see over here is the pins for you to attach to have that circuit going on. And a number of these packages can be interconnected, which means that you can put them side by side on a printed circuit board to produce larger and more complex circuits. Okay. So here we have a very interesting graph. So we started with the first working transistors back in 1947, and we only used 1 transistor, sadly. But as time moved on, we saw the increase in number of transistors being used. And in 1955-ish, there was the invention of integrated circuit, which means that we were using a lot of transistors or microelectronics. And then in 1965, we saw that the number of transistors used increased to 1,000 transistors, and this number keeps on increasing linearly, as you can see in this graph. Here, the graph that they've given us only goes up to 2011, and at that point in year, they were already using more than 10 billion transistors, which is really amazing if you think about it. How did we start from a single transistor and now we are using billions of transistors? So humans are smart. Don't misuse the intelligence. Okay, moving on. So we're going to talk about Moore's law. What is Moore's law? So Moore's law, Moore's law is based by Gordon Moore. He was the co-founder of Intel. This was back in 1965. So he observed the number of transistors that could be put on a single chip was doubling every year. He said that the number of transistors that could be put on a single chip was doubling. For example, if in 1965, it was 1,000, he said was doubling every year. So in 1966, he said that it would become double, right? So 1,000 becomes 2,000. And in 1967, it would become 4,000. 1968, it would become 8,000. 1969, it would become 16,000. 1970, it would become 32,000. So let's see if we got that right. 1970, 32,000. Hopefully that's right. If it's not, then it's okay. It's just a law. So in 1970, 32. No, I don't think we got it right, guys. Sadly. So let's do it again. So 66 would be 2,000, 67, 4,000, and then 68 would be 8,000, 69 would be 16,000. So that's not the case, isn't it? Let's see what they have to say about that. But the pace slowed to doubling every 18 months in the 1970s but has sustained that rate ever since. I did that on purpose. So the pace actually slowed down after he said that. I don't know why. But after he said that, the pace suddenly slowed down, which meant that what he said was it wasn't doubling. In fact, it was only doubling after 18 months. 18 months is more than a year, right? That is 1.5 years. So after 1.5 years, then it becomes 2,000. After 3 years, it becomes 4,000. And then after 4.5 years, it would become 8,000. And after 6 years, it would become 16,000. Okay, so after he said that, the pace actually slowed down, but the rate has become that way ever since. So what are the consequences of Moore's law? So the cost of computer logic and memory circuitry has fallen at a dramatic rate, because after he predicted this, people were saying like, okay, so if it is supposed to be doubling, then the cost should match the technology, right? This is why we can see that even though our computer keeps on being upgraded to having better memory, to being faster, the price is always at that similar range. If you notice, this is because of Moore's law. Because of his prediction, we are able to control the value of the market, right? So the electrical path length is shortened, increasing the operating speed, and also computer becomes smaller and is more convenient to use in a variety of environments. It becomes portable. Because Gordon Moore said you get to put more transistors. It means that it's going to be a better computer over time, right? And then there is a reduction in power and also cooling requirements because it has a smaller area, and then fewer interchip connections. Okay, so I'm going to cut it over here and continue in part number 2. So I'll see you in part number 2 in a bit. Bye guys. Take care. Bye-bye.